Let us understand the principle of superposition of waves. Let us consider that two waves are traveling simultaneously along the same stretched string in opposite directions. This animation depicts the state of displacement of various elements of the string at different time instant. When the two disturbances overlap, they give a complicated pattern as shown in C in region D. They have passed each other and proceed unchanged. Now, in mathematical form, when the pulses overlap, the resultant displacement is the algebraic sum of the displacement due to each pulse. This is known as the principle of superposition of waves. Let y1 x, t and y2 x, t be the displacements due to two waves disturbance in the medium. The displacement y, x, t of an element of the string when the wave overlap is then given by y x, t equals to y1 x, t plus y2 x, t. The principle implies that the overlapping waves do not in any way alter the travel of each other. If we have two or more waves moving in the medium, the resultant waveform is the sum of wave function of individual waves. Y equals to f1 x minus vt plus f2 x minus vt and so on up till fn x minus vt equals to sigma I equals to 1 to n fi x minus vt. In this animation, blue line represents wave 1, whereas pink line wave 2 and black line is addition of wave 1 and wave 2. Let a wave traveling along a stretched string be given by y1 x, t equals to a sine kx minus omega t and another wave shifted from the first by a phase phi. y2 x, t equals to a sine kx minus omega t plus phi. Both the waves have the same omega, same angular wave number k, same wavelength and the same amplitude a. They travel in the positive direction of x-axis with the same speed. The net displacement is then, by the principle of superposition, given by y x, t equals to a sine kx minus omega t plus a sine kx minus omega t plus phi. Using the trigonometric relation, sine alpha plus sine beta equals to 2 sine half of alpha plus beta cos half of alpha minus beta. We get y x, t equals to 2a cos half of phi sine kx minus omega t plus half of phi. The resulting wave is traveling in the positive direction of x-axis with the same frequency and wavelength. However, its initial phase angle is half of phi. Its amplitude is changes to a phi equals to 2a cos half of phi. If phi equals to 0, that is, the two waves are in phase, y x, t equals to 2a sine kx minus omega t. The amplitude of the resultant wave is 2a, which is the largest possible value of a phi. If phi equals to pi, the two waves are completely out of phase. The amplitude of the resultant wave reduces to 0. We then have for all x and t, y x, t equals to 0. Two identical sinusoidal waves, y1 as a function of x, t and y2 to the function of x, t travel along a straight string in the positive direction of x-axis. They give rise to a resultant wave y of x comma t. The phase difference between the two waves is a0 and b pi or 180 odd degree. The corresponding resultant waves are shown in C and D.